Hi all, we're back with intermolecular forces now. So you've already decided whether it's a molecule by deciding if it's ionic, covalent or metallic. Once it's covalent, you know it's a molecule. Then once you know that it's a molecule, the next thing you had to do was decide if the molecule is polar or non-polar. So just quickly telling you what we're going to do in this chapter is if the molecule is then non-polar, your life is very easy because there's only one type of intermolecular force that you can have for a non-polar molecule. But if your molecule is polar, you're going to see that we have two types of intermolecular forces. They're basically the same, but the one is a special one. So it's either going to be a dipole-dipole intermolecular force. I'm using abbreviations because it's just easier for me to write, but you must write out the words, sorry. And the other one is a hydrogen bond intermolecular force, which you will see now when I explain it in detail, that the hydrogen bond intermolecular force is just a special type of dipole-dipole intermolecular force. So for each of these, I'm also going to abbreviate intermolecular forces IMF. It's not a standard abbreviation, but if you give a key in the beginning of the question, you're also welcome to abbreviation. So let's start then with our intermolecular forces, and we're going to start by saying what happens if it is a polar molecule. So now you've already answered that question. You've said it is a polar molecule, so it's going to be either one of these two that we said. It's either going to be a dipole-dipole intermolecular force or a hydrogen intermolecular force. So let's start by saying what is a dipole-dipole intermolecular force. Always for polar molecules. So we're going to start by saying if it's a polar molecule, you already know that we've got a molecule, and that molecule has you've already determined that it's got a delta negative side and it's got a delta positive side. And I've mentioned in the previous video that if it's got a delta positive and a delta negative, we also call it a dipole. Dipole because di means two and it's got two poles, so therefore it's a dipole. Now, in intermolecular forces, you will see that you can't have just one little molecule. So in a substance, you're going to have the same molecule always right next to it, because you're going to have intermolecular forces within a substance. So let's say this was HCl, and we've already decided that it's a polar molecule. Then, as you've learned in electrostatics just now, this positive side will be attracted to the negative side of the next molecule. So here I will have a delta negative, and here I will have the delta positive of the next molecule. Because that's also a dipole, very, very intelligently, they have decided to call this a dipole-dipole intermolecular force. So the dipole-dipole intermolecular force is plain, simple, between two dipoles, two molecules that are polar, and then one's negative side will be attracted to the other's positive side within the molecule. So that's for dipole-dipole forces. Oh, just one more thing. You need to make sure that you understand that the intermolecular force is there. It's between the two molecules. It's not inside the molecule. It's between the two molecules. There is my intermolecular force. And please always think about that when you speak about intermolecular force. It's not inside the molecule. That's bonding. It's between the molecules. So we already said that for polar molecules, it's either going to be dipole-dipole or hydrogen bonding. Now, hydrogen bonding is just a special dipole-dipole, like I've already mentioned. So what you will see is that it's hydrogen always combining with one other atom. And these atoms are special. Hydrogen is firstly special because it's only got one electron. So it can only share one electron with another atom's other electron. So you will see these other electrons are only N, O, and F. Now these atoms are special because they are small, number one, and they have a very high electronegativity. Now the small part means that they only have one energy level between the outside electrons and the nucleus. So that means that the nucleus attracts the shared pair much stronger, which you also see in the higher electronegativity. So because those electrons there in the middle are not being shared evenly, you already know it's a dipole, so therefore it is a dipole-dipole bond. But around this hydrogen, there are no other electrons left. So when that electron is pulled over and forms a dipole with an NO or F atom, that hydrogen is left with no electrons, and you'll see some textbooks even call it a naked proton that is left there. So this delta negative is this delta positive is still a delta positive. This delta negative is still a delta negative because it's still a dipole, but these delta negatives and delta positives are just a little bit stronger than the normal dipole-dipole, and therefore you need to know that hydrogen bond intermolecular forces are always going to be stronger than normal dipole-dipole forces. So what happens here is that it's hydrogen, like I said, and NO or F. So you have your one dipole, and you've got your, let's use water, so you've got oxygen, and you've got a hydrogen, and you've got a hydrogen. So what now happens is that this side is my delta negative, and this side is my delta positive. But now what you can see is that this negative side of, let me just use the highlighter again, this negative side of my molecule will be attracted to the positive side of the next molecule. So if I have another water molecule, it will be attracted to a hydrogen side of the next molecule. And if I, oh, that's a very ugly molecule, let's just fix it up a little bit. So, like I said, it will be attracted to the hydrogen side of another molecule, which then would form another molecule like this. And again, this oxygen will be attracted to the hydrogen side of another molecule, and that's how it carries on. So you have these hydrogen intermolecular forces happening everywhere in this molecule. But also note that between this hydrogen and another oxygen, there could be a hydrogen bond. Between this oxygen and another hydrogen, there could be a hydrogen bond. And between this hydrogen and another oxygen, there can be another hydrogen bond. So this one molecule, for instance here, can form 1, 2, 3 hydrogen bonds. So keep that in mind when they ask you to compare substances that has hydrogen bonds, because there are only 3. There are only 3 substances that can have a hydrogen bond. So we already know it's hydrogen with the 3 other substances. So we know it's N, O, and F. So if it's with N, it's going to be NH3. If it's O, it's going to be H2O. And if it's F, it's just going to be HF. So please quickly look and see that you can see that if I'm looking at this molecule here, how many hydrogen bonds are possible? I've got a nitrogen that can connect with other hydrogens. I've got 3 hydrogens that can connect with other nitrogens. And therefore here, I can actually have 4 hydrogen bonds. Where in H2O, I've got the 2 hydrogens and the 1 oxygen. So here I can form 3 hydrogen bonds. And in the HF, I can only form 2 hydrogen bonds. So keep that in mind when you're looking at the hydrogen bonding. Alright, so that's hydrogen bonding. Please remember, hydrogen bonding stronger than normal dipole-dipole forces, and we have distinguished between polar molecules. If it's a polar molecule, then it's either dipole-dipole or hydrogen bonding. You're going to spot hydrogen bonding by looking for hydrogen bonding with either N, O, or F. And hydrogen bonding is stronger. So now we can move on to nonpolar molecules. So if we look at nonpolar molecules, I told you already your life is easy because there's only one type of intermolecular force that we can have there. So for nonpolar molecules, it means we have a molecule that has evenly spread out electrons. So let's say it was something like iodine, for instance. I've got an I and an I. And then I've got electrons moving around this iodine, and you know already that the pair that are being shared here in the middle, that pair will be shared evenly because they've got the same electronegativity, symmetrical molecule, nonpolar. So there's no side that's more negative than the other side. So if I have another iodine molecule next to it, it doesn't really want to attract this iodine molecule because there's no force really, there's no negative and no positive. And you will see therefore these nonpolar molecules are normally liquids or gases, mostly gases, because the forces there are very weak. But now how does that force actually even exist? So what happens is, because these electrons move at the speed of light, there can be a split second where there now are more electrons on this side of this molecule than on the other side of the molecule. So it makes this side of my molecule now, there I moved everything around, makes this side of my molecule a little bit more positive, and it makes it negative because there's more electrons, and this side of my molecule a little bit more positive. So I get a delta negative because the electrons are there, and I get a delta positive, but please, this is not a real dipole. So we call it a temporary dipole. And because it's a temporary dipole, it's there for a split second, and it's a very weak force still. But while it's there for the split second, on this side, in this other molecule, the negative side of this molecule is going to repel electrons over to that side, which means now electrons are going to be on this side more than on that side, and this side of my molecule will again be delta positive. So I've got a delta positive side here for a split second. So for that split second, I now have a force between the delta negative of this side and the delta positive of the other side. And the weak London force is therefore here between the temporary dipole and what we call an induced dipole. So this dipole wasn't there before. Remember when you did electrostatics, when there was a charge induced by something else, it wasn't actually there before, you made it. So it's the same here. So we formed a dipole by the temporary dipole that was there. So it's an induced dipole, and therefore there's a force for a split second. But please remember that these forces, that force there between the polar, the delta negative and the delta positive side, because it's temporary and induced dipoles, this force is very weak, and therefore these are normally gases. Now what you need to remember about these London forces, they trick you sometimes in questions, because you need to remember that all molecules have electrons, because there's electrons moving around in all molecules. So if I look at these molecules here, even though the dominant force was hydrogen bonding, there is still some London forces as well. So sometimes you're not going to be able to explain the difference between two things, because they might both have hydrogen bonding. And then you have to look at how many electrons are there, because if there are more electrons, then these electrons move around more temporary dipoles can form, and more induced dipoles can form. So please, you need to keep in mind that any of these dipoles, hydrogen bonding, even if those are the dominant intermolecular force, there will always be some added weak London forces. So yeah, keep a lookout for that. Now we have to just see how are they going to ask these questions. They're normally going to say to you, use intermolecular forces to determine whether something has a higher boiling point than something else, or whether something has a lower boiling point than something else. Oh, now I'm struggling to get to the next page. There we go. So I've done it here for you that you can see the steps in which you should answer. The first step is we're going to determine the polarity of the molecule. You already know how to do that. The second step is you're going to name the different type of intermolecular force in each of the molecules. Then you're going to decide which one has the strongest intermolecular force. And the last step, please don't leave that out. If it has stronger intermolecular forces, then it needs more energy to overcome these stronger intermolecular forces. And more energy needed means I'm going to have a higher boiling point, or I'm going to have a higher melting point. Just read the question and see which one they are asking about. So step by step, you will get your marks, and you will see that in the exam these normally count 4 marks, and then you'll know you have to go through the thinking here and decide for yourself then which one is has the highest boiling point or the lowest boiling point. So let's look at this example, and we're going to try and score 4 marks for this question. So if we look at the example there, we say, they ask us, why is water a liquid at room temperature and carbon dioxide a gas? So actually what they're trying to ask you is the boiling point of water is going to be much higher than the boiling point of carbon dioxide. Because if carbon dioxide is a gas at room temperature, it's already boiled at room temperature. So we're going to do it step by step, and you are welcome to write it out like this. You can write the one molecule, and you can write the other molecule, and once you've written it, it's also easier to see what the Lewis structure, you can even do the Lewis structures if you're not 100% sure, because it always helps with the polarity. So the first step 1 at the top there says, determine the polarity of the molecule. So for water, we know it's a polar molecule. For carbon dioxide, we know it's a non-polar molecule. Then we have to look at step number 2. Because it's a polar molecule, we had 2 choices. It was either dipole-dipole or hydrogen bonding. But I've said to you, it should scream at you if you see hydrogen and oxygen, because it's NO or F, and therefore it's going to be a hydrogen bond intermolecular force. Please remember to add intermolecular force, because it's not really a bond, because that's inside, remember. Okay, so carbon dioxide makes our life easy, because as soon as it's a non-polar molecule, we know it's going to be weak, and you don't really have to add the word weak. I just add it because then you know already it's going to be a weak force. Weak London intermolecular forces present between these molecules. That's 2 marks already, because actually it's already 2 marks already, because you've done step number 1 and step number 2. Now we're going to look at step number 3. Which of these are stronger? And you can clearly see that hydrogen bonding is the strongest dipole force, and the other one is weak dipole force. So you're going to say hydrogen bond intermolecular forces are stronger, please write this in a full sentence, are stronger than the weak London intermolecular forces. I promise I'm going to get another pen, because this one is really not nice. Is stronger than weak London intermolecular forces. And then don't forget the last step, because then you have to say, therefore, and you're allowed to use the 3 dots in science, therefore, more energy is needed to overcome these stronger, now I can't even spell energy, more energy is needed to overcome these stronger intermolecular forces, and therefore I'm going to have a higher boiling point for water, and it's going to be a liquid at room temperature. So you can see now what they're going to allocate the marks for. You're going to get 1 mark for saying the polarity, so it's polar and a hydrogen bond. This one is non-polar, therefore weak London forces. Always name the forces. Then for comparing, you said hydrogen intermolecular forces are stronger. There you get your another mark, and then your last mark, don't forget it, more energy is required to overcome these stronger intermolecular forces to give us a higher boiling point. And you will see in the exam, a question like this is then 4 marks. In the next lesson, I'm going to talk quickly about, give you a quick summary, and then we're going to look at the physical properties and do some past paper questions on this topic, and then the chapter.